All right, let's go. Okay, so I have a couple of things to go through. So we're going to finish off this piece about robustness, which is this interesting mechanism for producing power laws. And the next piece here is to contrast it with what's called self-organized criticality, which I've introduced to you. So, and then we'll move on to strange other kinds of distributions that appear from mechanisms that are just slight changes, right? There are slight changes in the details of these mechanisms, and sometimes you get power laws, sometimes you get Lognormals, sometimes you get other things. So it's just a good, this is just a warning, right? Just be careful. I mean, this is a gigantic field of things that we're talking about, and I have to kind of touch on things, just brush up against them, I suppose. But so that'll be a warning piece. And there's some nice, fun math involved. Okay, so yeah, and then we go into complex networks, which will be fantastic. All right, let's see. So self-organized criticality. So here's the emblematic example of it. This is from the 80s. Lots of great things in the 80s. So you've got a sand pile, right? And you're dropping sand down. You have your graduate student up here who's like titrating little bits of sand in here, and they're just stressing out. They're probably watching Breaking Bad or something. Okay, so it's the 1980s. So they're, I don't know, the original Battlestar Galactica or something. A-Team, there you go, great. But only when it's on, right? They can't watch it on the little screens. It's pretty awful. Maybe they read books, I don't know. So they're doing this, and then they're looking at the avalanches that form, right? So eventually, there's the idea in landscapes of the angle of repose. So things are settled. If it gets too steep, then stuff spills down. And so you carefully go and measure how big that avalanche was. And so the idea is, or this observation apparently of sand piles, is that you would get avalanches of all sizes, which sort of fits in with all of these other power law things, right? Like we talked about, of course, earthquakes. I mean, very natural disasters, very much a feature of natural disasters, these heavy tail distributions. Okay, so there's that. It turns out, so this inspired a model that looks like this. Okay, so here's this model, and it's per Bach and two colleagues. I think it's 87, published in Physical Review Letters, very influential. So this is a model of this sand pile. This is how it works. You drop a little block of sand, so now sand is a block, and there's no graduate student, there's just a computer. It falls down, and there's only one rule. If it lands on a little pile of sand that's 3 high, right? So this goes to, they jump out into the adjacent squares, so it collapses. This is a way of creating a collapse, right? So that's a funny looking thing. So if there were 3 here, then it comes along, another one lands on it, then you get 1, 1, 1 here, and 0. If there was nothing else, right? Now, if you started with, look at this video I'm making, 3, and there was a 2 here, and 1 here, and 1 here, and maybe a 3 here, drop 1 on this guy, it becomes a 0, and these all increment, which is really weird. Somehow the sand pops up on top of the others. Okay. This becomes a 4, so that splits, so that becomes a 1 here, 0, 1, 1, 1. So you see how you can get cascading behavior. All right, so the idea is how big is that potentially an avalanche? That's the model. So there's no pile of sand. It's like some sort of weird carpet that falls over, splatters around. This is the model, just so we know. It's not this. Extra problem, people couldn't actually get sand piles to do this. Right? This was not sort of a repeatable thing. It turns out one experiment, and this was controversial, but I think it's true. It was Jens Feder's group in Norway. Again, the victims here are graduate students. And the unsung heroes of science. They put 2 plexiglass sheets, and they got rice, and dropped rice in from one corner, and let it fill up, and then counted how much rice came out the end when it collapsed. So they played around with different grains. It turns out it only works for long grain rice, not short grain. They managed to produce in this 2D system power law size distributions. Some arguing and so on. I remember being on this is 1995 or 6, a conference on granular media in Corsica, which Corsica was really the great part of that conference for a couple of weeks. Lots of arguments between physicists and engineers about all this madness. granular media, right? It's a big deal. So just trying to understand sand piles turns out to be a big deal. Okay, so it's a very funny kind of history. There's a lot more to it, but this is sort of the seed of everything. Actual sand piles, crazy model which doesn't look like this, which doesn't do what people thought it did, and then there's sort of this one that, people managed to make work. All right, so from this comes this idea of self-organized criticality, and I drew these pictures up here before, so this is for percolation. So there's this transition here from all of the clumps being small, macroscopically small, to one of them being dominant, right? And so that's the phase transition point, the critical point. And self-organized criticality means that instead of having, so here we have a dial, right? We have P, this is a dial. We're dialing the probability that a site is occupied or not, that it has a tree in it or not, right? We just tune it. There's no, that tuning is us. We're we're driving the thing. Self-organized criticality means that nature somehow self-tunes itself, or some of these natural systems, or maybe human systems, self-tune themselves to get to that point. And you get all sorts of nice metaphors, like the boundary between chaos and order, right? This sort of edge, right? The edge of chaos and order. That this is good because on one side it's too messy, on the other side it's too ordered. This is where the good things happen. So it's very appealing. It's very appealing. So the big argument, and we'll say this again, from the hot model is that this is a little crazy and that you can get these parallel size distributions from a much more not to use the word again, but kind of robust mechanism for producing them. That's not as sort of special. Okay, so here it is. So they're dissipative, right? So they're being driven in some way, or pouring things onto this sand pile. Somehow they get to a critical state. So the Ising model with the temperature is being self-tuned. Somehow the whole system is controlling its own temperature. Right, that would be the equivalent thing. So you're getting these parallel size distributions out for free. So it's Bach, Tang, and Weisenfeld. This is 1987. There you go, all sorts of, this is the paper. This is the original paper, right, good. Lots and lots of work about this. So the problem is that you have to be right at this state, or very close to it, right? You have these distributions very close to it. If you move off too far this way, suddenly you have these kind of distributions. If you move off this way, you get this, this giant piece and smaller guys. So it's mathematically, it's just one point, right? Measure zero, right? Measure theory, yes. So it's not always clear that there's a self-tuning mechanism there. I mean, it's appealing. Lots and lots of people going berserk about this for a long time. Lots of criticism. Okay, and here's sort of the upshot of it. Per Bach, who is no longer with us. He was a a nice character, but sort of I think he had what you in sports you would call white line fever, if you know about this, right? That term? No? Okay, so white line fever means you're a lovely person off the field, but you cross the line onto the thing and you're a monster. Yeah, there are some people who get it, and they really get it. They have a beer with you later on, but they tried to kill you just a couple hours ago. Which is interesting. Okay, so in what I mean by that is in conferences, he would really go at people, in the great spirit of academia, right, where it really matters, yeah. But all right off the field. So how nature works, boom. There you go. Produce a body of theory so that you end up with a book that has that title. That's pretty intense. So you can see there's the, I don't know if that's a sample, but there's right here are dunes and things, and there's a lot of natural stuff in here. So this is that's a strong title. Okay.
Did he work
with what?
Wolfram?
Oh, I don't know if there's a connection. Yeah. No, I think they have different.
They probably hate each other, right? Because they both want to have the master theory.
Well, I guess, yeah. Yeah. I mean, they're different stories, right? This is a traditional kind of physics story, StatMech. Wolfram's is that discreteness controls the world. Which has some people, right? It from bit, there's that whole business, right? I mean, it is weird, right? I mean, we don't really understand things like gravity. And we have great models for it, but we don't quite understand it. So there's all sorts of stuff about information, giving rise to anyway. All right, fine. So all right, both of these things produce power laws. They're sort of put up against each other. At least they're three-lettered acronyms. TLA, three-letter acronym, right? Optimization versus self-tuning. It's an old one. Okay, it's not mine. What's that? Yeah, right. I mean, there are lots of these, like GNU. GNU's not Unix. Okay. Which one? What's that one? Oh, Windows. Okay. Right, which still exists, right? Yeah. Cool. So there's optimization versus self-tuning that this somehow has to be. You should be able to see that. Hot systems, of course, we saw this that they work over many different densities. We should really. It'd be great to produce model, like get a functioning model of it. To be honest, you're going to do it for 1D, but we need the 2D. Let's see. So. These guys have one special density, right? There's really, whatever's going on, it has to get to this special density. And the point I made earlier was that the structure is random there. It's still a high entropy kind of structure, right? So there's a power law size distribution of forests, if you like, but they're all messy shapes, right? They're featureless. Whereas the hot systems produce these low entropy, very specialized, they've evolved to fit the problem, whatever it is. It's the environment, if you like. Whereas you get generic structures coming out of SOC. And I think I have, okay, this is from, of course, this is from one side. This is from Doyle and Carlson. And so, yeah, comparison of these two things, right? So, robust yet fragile from hot. So it's hot and data. So hot and the truth. Hot and reality is the way they framed this. Yeah. Your theory, my theory, and reality. Yeah. It's great. These are homogeneous in their nature. These are very heterogeneous. There's low entropy, as I said. They're structured. Lots of things here. That's true. So the maximum event size is not going to be large for these. It is going to be definitely large for these if they blow up. Other things. There are lots of other bits and pieces here. Yeah. Mechanism for power loss, right? It's just somehow fluctuations, robust performance. Lots of good things. Yeah. All right. Kind of covered all this. Okay, so that's true. So the largest event shape is fractal in these. So right at the critical point, you get a almost percolating thing, which is fractal in nature. It's this tendril-y kind of thing. As you go above it, it starts. You can see it you see a blob from the outside. You see a blob. Below it, you don't see any big thing. Right at the critical point, you'll see a spidery, like a tendril-y looking thing, because it's going, So in fact, the size of the giant component scales as it's proportional to the number of trees above the threshold, right? So it's a macroscopic piece. At the threshold, it scales as some power of the number, right? Some power lower than 1. Fractal. Okay. This is a good thing to read. Compact. So So remember this guy here, the forest, like this, the forest boundaries, the forest fire breaks. This thing is the biggest guy, right? And these are all compact shapes. I mean, meaning that they're not. I guess that's maybe a bit of a questionable use of the word compact, but they don't look like this. Right? The biggest forest would look like this. The biggest forest for this is more of a blob. And above the critical point, SOC produces this kind of thing as well, sort of, with little. Okay, you should read this. This is a fun paper to read. I know you're thrilled about this stuff, but you should check this out. Click and read. It was in Proceedings of National Academy of Science, so it's a summary piece, right? Good. Okay, 2 last pieces in all of this are cold theory, all right, because we are funny. This is Newman and co. So it's constrained optimization with limited deviations. Right? Sounds like someone worked hard to make an acronym for cold. Okay. And so it's a simple variation of it, apart from the humor, which is just simply you say that the large losses, you're worried about them. You don't want the thing to completely explode. So it's robust yet fragile, but let's try to take the fragility out. What happens is if you start to say you punish so you've got some evolution of this thing, right? So we had the way those forest breaks, the fire breaks were being placed. If you have if you punish the algorithm so that it avoids having too large an area that could burn, you can do that. It will increase the average cluster size, right? So on average, your fires will be bigger. So you're giving something up on average, but you're going to take away the massive explosion. Okay. So you get this kind of thing. You get a truncation. So you get a power law size distribution. These things are very common in lots of different systems with an exponential cutoff, which seems like this would matter, but if your x sub c is quite large, for example, then x divided by x sub c, when this is x is much less than this guy, this thing is basically 1, right? So even though it is an exponential decay, this thing will dominate, and what you will see on a log-log plot is it looks like a power law, and then it goes boom. So this will be a minus gamma slope, and then exponential kicks in. Like it really kicks in. It's a very slowly decaying exponential. It's not at all felt until that, right? So this part dominates to start with, and then this goes. Okay. And as is typical with exponentials, e to the minus 1 is kind of like a tenth or 1 or 10 of things we're interested in those. Yeah, but when it's about 1, so when x is around x sub c, things are really starting to drop off. Okay, so we call it a cutoff scale. All right, lots of other things could pop up. Weibel distributions, look at this crazy guy, right? So there's a power law. You can see how you differentiate this thing is going to work, right? So this is going to, you could integrate this guy, it's integrable. So these are fun little beasts. It turns out that this is an expansion of the exponential distribution, which is a failure mechanism, which is what you're doing with those fires. It's a failure mechanism. So when gamma is 0, actually, you'll see there's e to the minus a, and this is just x, so it's e to the minus, so you recover the exponential. So this is a way of getting kind of a broader class of failure mechanisms, which people use to model all sorts of things in engineering. For Weibels? Yeah. Because of what?
Because you can model it via Weibel distributions, do you get like a time to event that go around?
Yeah, so this will be, so you'll see these for, yeah, right, probably a fair, like the time, lifespan sort of thing. Yeah, that's right. For light bulbs or large civilizations, whatever you're modeling, right? Randomly sample from it, yeah. Yeah, the sequester's on, so the joke is that math is also being turned off, right? So you just don't, your brains are off. You're not being funded by the government. Should use this. Okay, these are fun. So you might get these guys. Okay, so there's one last piece. We're going to get into network robustness. We'll come back to it later on. This paper has been cited 50 bazillion times. It's just unbelievable. I'll show you some massive citation numbers for papers that started complex networks. And one of them is a guy I used to work with, Duncan Watts. So I think I update them every time I give these lectures. So it's up to 20,000. So we'll see that. That's pretty good. Pretty good. Given that getting to 10 is considered to be, like an achievement on Google Scholar. They tally the number of papers you have that have been cited 10 times. 20,000 is pretty solid. Okay, it means you've started a whole field, basically. Okay, so I'm just throwing this, I guess, into the robustness story. And maybe I should have put it later on. Oh yeah, so the way I'm doing this is I'm going to bring this back later on. I just want to mention it. It is about robustness. We're going to go through networks, and then we'll talk about it later on. I've had this in different places. But it's a good story, right? We start to understand what real networks are like, and then simple questions like, what happens if we attack them, right? We take things out. Okay. Which ones blow up? I have a terribly ridiculous thing to finish this. This is like a mental health break, if that's all right. Is that all right? And then we'll go on to the Lognormals, which is a hairy business. Always good with the hairy business. Okay, so I think this will work. Wow. Wow, I just turned it up to some giant amount.
Hold the elevator. I'll remember this. What's your ID number?
It's 1142. Eat my ass.
Come on, come on, come on.
Pretty rude.
Oh, I'll get the next one.
Plenty of room.
No, I'll just take the escalator.
Please on in.
I'd rather my robes didn't smell like a fillet of fish all day, thanks.
That's hurtful, man.
Well, next time, just let it go. Let it go.
Sorry.
My lord.
Stormtrooper.
My lord.
Stormtrooper.
My lord.
Stormtrooper.
My lord.
Yup.
My lord.
Uh-huh.
My lord.
Yo.
My lord. My lord.
Stormtrooper.
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 My lord.
Stormtrooper. Stormtrooper. Stormtrooper.
My lord.
Ugh.
My lord.
Go yourself.
My lord.
Go yourself.
My lord.
Go yourself.
My lord.
Go yourself.
Aw.
You got hurt, I feel.
What's up?
All right, sorry. Okay. See? Refresh, right? What's that? You could have a nap instead, I suppose. But what's that? They did look a bit Udish. I'm not sure who those guys are. I have one of my people is pretty fond of Oods, I have to say. I'm not sure why. I think because that would be a weird thing to do. That's the appeal. Right? Okay. Little mental health break. Okay. Lognormals. All right. Actually, before we do that, I have a couple of... So really, another fun and kind of interesting power law thing is the baby name stuff, right? So there's some really good visualizations on this. But it is kind of crazy what... So Michael. Okay. So this is out of, per million babies, 20,000, right? 20,000. I mean, it's an incredibly skewed distribution. You only have to go to about 1,000, 2,000 names, and you start getting things that are basically misspellings. And it's, yeah, we're incredibly coherent. And in some countries, of course, there are rules, right? I think Germany, is that right? You aren't allowed to name your kid anything. There's sort of a list of names.
In Italy,
Italy?
if you have a girl, you're not allowed to name her Luca. It's a boy's name.
Okay, so there are rules, and people have some arguments about it, and they come up with some really out there names. This is.
Part of this, I don't, is that a parallel distribution?
Oh no, the number of time, right? Yeah, if you rank people, right? If you rank names, I mean, it's a very skewed distribution. So there's a lot of copying going on, which is really what, especially for social phenomena, it suggests straight away, right? The mechanism is a copying one. So, so this is my wife's name, so it took a bit of a hit. But this is really a fun thing. Yeah, we'll do that for you, right? Gertrude, gone. Just gone. No more Gerties or Trudies.
What about lifespans of names?
Yeah, so there's a whole thing there, right? I mean, and so this has actually been the data set that people have really studied for a long time for culture, because it's been the data set, one of the great data sets we've been able to get at. Now we have things like Google Books, which of course has their own problems and all sorts of things, but there's more stuff over long, long periods of time. Yeah, so boys here, and girls here. Yeah.
It is implicitly aggressive. What about in recent history?
That's right. So it's blue back here, right? Yeah, and then it was co-opted. Yeah. Yeah. So yeah, this one's not going to work out. It's just a no. Actually, is a boy's name, but the same thing happened. Yeah. So there were a couple of good ones. There's always this, right? People are trying to make their kids different.
Yeah, what about...
These are awesome. So these are some unusual ones. Just enjoy this is basically what I'm saying. Rogue for a girl. Lilo? Where's Lilo? Oh, not Lilo and Stitch, right? Shug, Sesame, Ami, Vanille, Vanique. So there are usually a couple of hundred uniques every year. There are usually a couple of, usually a couple of hundred uniques, which is good. So the boys ones are great. Casanova. Casanova. Let me frame your life for you. Let me frame middle school for you and college. And
Google.
yes. Good luck. Haven't with a T at the end. That's, yeah.
I get the rest of the name.
Hippo is pretty rough. Hurricane is pretty rough. I mean, it's bad enough having a name like Sandy when it's,
Yeah.
right? That's a real problem. Like they may have to get rid of that because people get picked on.
Video about people named Sandy
Who really got
who got
impacted.
comedic video.
Oh, it was comedic. But
the negative impacts of Hurricane Sandy.
no, it's really kind of a problem. Yeah. They may have to change it because it actually...
Named like unpopular political figures, like Hurricane Hitler or something like that.
Right, you could get... Okay, I guess it would be a little thematic, but you could get the worst people ever, right?
Yeah.
And just repeat them every year. Like B is always the same one.
What's nefarious?
Like, Bundy. What's that?
Mowgli? Like,
Yeah, from the Jungle Book.
alright, that's alright. Did you send this to Nick?
So this is very tangential, but Mowgli, written by... So he lived in Vermont. Do you know this? He lived here and he really liked it. His wife was American. And then he had to go back because something went wrong with her family. But he would have stayed here. There's a house in southern Vermont that he lived in. Yeah. Thunder, Tron, Turbo, Vice. Oh, it's great. Xenon. It's pretty cool. Mango, that just seems... I don't know what to do with that. Really.
Wait, do you know the guy's name?
Burger.
So when I was in there was this movie called Xenon Girl of the 21st Century or something.
Yeah.
And she lived in the, it's a Disney Channel movie, and she lived in the space station.
It's not good.
But it was a girl. Like,
Okay, so these are fun. So that's the thing. People are trying to distinguish themselves, and I think the example here of Michael, partly it's a mixture of there's a tiny slither there of girls called Michael, but it's this is culture. I mean, this is the immigration. People are right. There's a lot more people from different backgrounds with different lots of sets of names, but there's also just more awareness. Like you're more aware of the world, right? So you start changing your names a little more. Anyway, all right. That is it's a really interesting example. Okay, that was fun.
did you send this to Nick and Lois?
Oh yeah, you got to be careful with that. Yeah, of course, the ones you choose, you think you heard it once or something. If you hear something once, it means it's everywhere. That's a bit of a like this network story. If you hear something once, there's a very good chance that it's actually, you got to be careful with that. So, yeah, I mean, we named our kids in some ways, and of course, it was part of the thing that was going on. Yeah. All right. So even if you try not to, it's very hard. You could just make up. So you just make
This is really bluntly known as the character.
okay.
I'm sure they'll be okay.
And I'll show this later on. Okay, good. All right, so that was a little, like the power laws. So there's another power law example. All right. Okay, so lognormals, these things. I'm going to talk a little bit about, simply what they are, how these can be confused with power laws. This is just good. You should know this. And a couple of other little growth models, right? Just small variations, get very different outcomes. And then we'll be done with this and we'll move on to networks, which will, retrieve some of the stuff we've had already because that's the way it works. But okay, log normal distribution. So there are other things that can be heavy-tailed. It's a bit of a funny one. It can be heavy-tailed under certain, given the parameters of the right way, right? So this should look like a normal distribution to you because it certainly is. And it's a transformation, right? So instead of y minus u mu, we've got, we've made a transformation from y equals ln x. This thing is distributed normally, and then this is a log normal. And when you do dy dx to get the little Jacobian thing, 1 over x, you get 1 over x. So that's this little beast here. So Weibull distributions, we just mentioned them. These guys appear as well. The CCDF of that is a stretched exponential. CCDF of these things is more complicated. Gamma distributions, lots of other things. So we've seen the gamma function. It's the sort of the inside of those beasts. Lots of little beasts. Okay. So as I said, so log x is now distributed according, so log x is distributed according to a normal distribution. You see in a lot of different real world situations where again there's some sort of growth mechanism, but different to the one we've talked about with rich gets richer. It's just different kind of stories. We'll get to that. It's also explicitly for positive quantities, right? Which, so if you're talking about money, although you can have debt, of course, if you're talking about money, it's not a bad thing. Okay, here's the standard form. There's a bunch of things that come out of it. You can compute these. It's not a little bit of pain, but you could compute. So that actually the average of the thing. So the funny thing we do is we use the underlying normal distributions pieces, the standard deviation of sigma and the mean. If you compute the actual mean for the log normal, it's this little nasty thing. Median is this, the log, right? This is the actual standard deviation and so on. So they're tweaks. We don't want to actually live in that space too much. We're beholden to the normal, so we stay out there, all right? Very different to power laws. All the moments are finite, right? So for any power law distribution that keeps going, there's some order for which the moments are all infinite as you go beyond it, right? So that's a different feature. And this is the connection between these two. Okay, so I just said this on the board, right? So we have this guy is distributed normally, and then we're going to set y equal to log x. This is the sort of thing. All right, I wrote it on the board. dy dx equals 1 over x, boom, 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 and we get our normal distribution. And so a log normal distribution. This 1 over x is the little factor that can make things interesting, because it's x to the minus 1. All right. So here's an example where we have a log normal, which is in blue. Mu, the mean is for the underlying distribution, mu is 0. So the actual mean is different to that. Sigma is 10, so it's kind of a wide standard deviation. And we've got a power law with gamma equals 1 and a prefactor of 0.03. So the power law is a perfect straight line on this thing. This guy's got a little bit of a curve on it, but you know, if you're doing your regressions and so on, these things are messy, you've sampled from them, there's a chance you get it all wrong. And this is right? This is pretty good over 4 orders of magnitude, and usually people are sloppy enough to say, it's okay. Right? It's a little scary, So this is kind of what's happening. I think we can go through this reasonable speed. So we have, if we take the distribution, the log normal, take the log of it. So let's see what's going to pop out. So there's a 1 over x. So log of 1 over x becomes minus log x, right? Because we're going to put the x on top, minus sign at the front. It's x to the minus 1, so the minus 1 comes down. These are products, so everything's breaking out into a sum. There's minus log of root 2 pi. And I think I lost the sigma. Oh, so bad. Just write on it. There was this talk years ago where there was a mistake and the guy goes, with a big, and the crowd, you know, mathematicians like, no! Okay. You know, he's got a, Sharpie, right, it's not going to end well. And this piece just comes down wholesale because it was an exponential, like that. So let's spread things around. So there's a log x. We can expand this. We'll get a log x squared. We'll get a minus 2 mu log x. And so we can group those guys. Okay, so there's a 1 over 2 sigma squared. Let's see if I've got this right now. So there's log x squared. That comes down to here. There was this minus log x. That's this piece. And there was, as I said, a 2 mu times log x. So these 2's cancel here. So we get 1 over sigma squared times mu of log x. So this is this blob here. And then a bunch of constants, which are still missing at sigma. Yeah. What's that? Consistent. Yeah. Dear. I'll be flogged. All right. So sigma squared, by me, it's okay. Sigma squared greater than or equal to 1, and mu, right? So if we have this, right, and sigma squared has to be much greater than mu, is what I'm trying to say here, right? So this is going to be small. Sorry, this is going to be small, and yep. And this is going to be small. That's the point. These guys are disappearing. Log x grows very slowly. Right? So this piece is going to be kind of out of the picture. This term's going to be out of the picture. We're going to get a minus log x plus a constant, so that's no big deal. Minus log x. So now that's right. So now it looks like it's a gamma of -1. This is our gamma here. So that was the example I gave you. Sigma was kind of large, so sigma was 10, so it's 100, much greater than or equal to 1. Mu was 0, so it's not an issue, right? So it's actually 0. In fact, it was 0 over 100, so that term's gone. This was 1 over 200, so you can see why this piece is out of the picture until log becomes quite large. So log grows slowly. You know, you can estimate when that might happen. So you need that, I don't know, let's say that the first term becomes 0.05 of the second term. So you can, you know, estimate that. Fine. No big deal. Okay, just messing around with this. This is not a big deal. But basically, yeah, so the transition when it starts to not look like a power law anymore, log 10x will be around 5% of, in our case, it was 100 minus mu. So that's not bad. That's a big number, right? Anyway, the upshot is you could find a -1 exponent, maybe, right? You're messing around. It could be a log normal. -1 is a bit of an extreme exponent for sure, but you could certainly have power laws with -1s and exponential cutoffs. That's actually quite, you know, that can be produced, right? All right. Okay, so let's produce these guys with a growth model, and then we'll tweak that and see very odd things happen. So this is a bit unsettling, basically, is what's going to happen. So very simple. The n+1th sample is going to be some random number times x sub n. So it's a little growth variable. It's just got to be greater than 0. You're allowed to have shrinkage in the Seinfeld sense. Okay. And so in log space, growth is by addition, right? So we take the log of this, log of xn+1, log n of r, plus log n of x. So this is, we're adding to this. So if this thing is, it doesn't have to be normally, if this thing has a finite variance, this little log r guy, right? Then we're adding and subtracting because now it's log. So if, so if r is less than 1, right, so it's shrinking, then this will be a negative quantity. If it's greater than 1, this will be positive. If it's equal to 1, this is just a 0. Makes sense? Then as long as this beast is distributed, you know, not too bad. Could be from any distribution you want. As long as it doesn't have a large variance, then you'll end up with log n of x eventually being distributed normally, right? So you run a lot of these. You have an x1, and you go and produce an xn. You have another x1, you go and produce another xn. You have another x1, you go and produce x. They're not competing against each other. It's just a random growth, random growth, random growth. Okay, you'll get a log. That's where you get log normals from. So it's an incredibly simple thing. How do you feel about this? No? So this is the central limit theorem, really. So, right, so you're just adding a little guy here. So if you add up all of these little samples, and R is being sampled from some distribution repeatedly. You know, the central limit theorem is generalizable, right? You can actually sample from slightly different distributions or a set of different. That's okay too. As long as nothing explodes too much, you'll get a normal distribution. So the log of the size becomes normal, meaning that you get a log normal for the size itself. Did I say that right? Okay, I don't know. All right. Here's an example of where we have some trouble. So this is 931, distribution of firm sizes, right? So another big system story. You've got all these different firms, some really big ones, some smaller ones. So it uses that argument that we just had to explain firm size distributions with gamma about 1, which is a bit funny. So this is a bit confusing to me, but so Rob Axtell, who's sort of a colleague, he spoke at our first TEDx conference, Big Data, Big Stories, a couple of years ago. He's at George Mason. He runs a computational social science program, PhD. Done lots and lots of interesting things, lots of simulations in social science phenomena as well. So so this is a paper that appeared in Science. Has a parallel fit with gamma equal 2, actually. So it's a different thing. This is actually from his thing. So this is, I think it's a 2, right? So this is actually 12 orders. This is pretty spectacular. 12 orders of magnitude. And I guess he has, right, so that's 10 to the 0 here, 10 to the 6. So there's 6 orders of magnitude here. So that's a -2 looking thing. So there's something going on, and we'll, what's that?
So are we getting like finite data size issues with the ends there?
There was something wrong. There's something slightly problematic with Chebrat thing. Oh, you mean up here?
And at the other end as well.
Yeah, so fully expected, right? So this is going to be this is perhaps you're just not getting all the firms for small ones. It's just harder.
Yeah.
Right, this is a firm of size 1.
Less than 10 to the -1. Wow.
What's that?
The best frequency.
Yeah, so this is normalized. So the whole thing should add up to 1. This is, these are, self-employed firms of size 1. So that's, sort of just a different game, right? I mean, it could have fit, but it could be more. You'd have to have some little, you have to think about what's going on here. Yeah, this is definitely rolling over here, but here to here, it's not bad. Many orders of magnitude too. So there's 10 to the 1. So let's say 4 orders of magnitude where it looks really solid. And then, fair enough that it rolls over or does something. I mean, it has to stop. Right? So unless we're all part of the Borg. This is what we're preventing with the shutdown, right? That we don't end up with a delta function here where everyone is working together. Right, so that is a problem. The Panda camera has been taken out. Oh my God. Wow.
Can't even look at pandas to cheer yourself up.
I didn't do that, so I might need to do that now. Now I feel I regret not doing it. Okay. Oh, there's a bit missing. Okay, so Chebrat seems to have something reasonable, which is the growth rates seem to be independent. I mean, you'd have to look at how these things grow. You need to track them over time. Doable, but hard, right? This is the sort of thing where you can see how you get one data set at one period of time. It's a census type thing. What you need is then that censusing to be going on over time, and you need to be able to track where firms go. So that's a lot of data, yeah. So here's the setup. So there's a Malkai et al. Paper from '99. The connection between them is a bit funny, but again, there's going to be a potential competitive piece in here. So let's have n things growing. They have, right, the ith one has size xit. Generally, we have this, which is what we had before, right, the log normal story. Okay, so there's going to be a tweak on that. So we know if we just run this with R being sampled from some benign distribution, then we get log normals. So we should get something that looks like it has gamma -1, or gamma equals 1, but -1 slope. But we know it's -2, so something's changing. I mean, that's a big change, -1 to -2, right? So everything's going to look the same, but we're going to change just one tiny piece. So there's a limit to how small the xi's can be. And it's a little bit of a funny mechanism, but the idea is the next value of xi for the ith firm is going to be the maximum of the growth one, which is what just the log normal story, plus some constant times the average size of what's there. Right? Not plus. It's the maximum of these two. Right? So that means it can't get too small. Right? So it gets really small, then there's this little shelf here, and this C can be tuned, so you can make it quite small. Basically, this is. While it does depend on everything that exists in the system right now, so this does actually move up and down. Essentially, you're creating a boundary away from 0. Right, so you've got this random growth, but things can't shrink down. There's some little boundary. That's all, right? That's all you're doing. And it can be really, really close to 0. Just moving it out a little bit. So should that matter, right? You'd kind of think, well, that probably, this is a very small change to the mechanism. And a lot of mechanisms are robust, right? You add a few little bits and pieces, same sort of thing. Universality story. Okay, so you can play around with that. some suffering. And you will get out, again, an x to the minus gamma. And you get this surprising little piece. So n is, again, the number of firms. Gammas are appearing here. This is c, which is that constant that's appearing in the time. You multiply that with the average firm size to get a lower limit. So if we have large n, we're going to be able to get rid of a few of these things. And if we have small c, we can also get rid of a few things. So let's do that. So in general, we can just say, yeah, so c over n is much less than 1. So if we do that, then this is going to go away, this is going to go away, and we can keep that one. No, let me... Is it arbitrary? Yeah.
Oh, you know what? It's okay. If you take c over n out of the denominator,
Yeah.
you're left with some large thing minus 1. So get rid of that 1.
I don't like what I've done there. Well, this should be... Go away. I may have to check that to make sure that's okay.
It's 0 over 0, right? So you have to do the Hopital's rule?
Well, this is going to become... Well, this will become... This is small,
Small.
minus 1.
Minus 1 over 0.
Whereas this thing is... So, depends on... Yeah. Yeah, that's right. If gamma is close to 2, then this is a nasty little business. That's a subtle point, but it's not going to... It isn't going to 0 over 0. Can't be doing that. This thing is going to become... Right, it is becoming small on the bottom, which is nasty. Minus 1 is correct on top. Why do I want to get rid of the gamma minus 1, 1? Does that seem right? It seems like that one is too... Okay, so it's okay if gamma is less than 2, right? Yeah, I mean, you're in trouble if gamma is equal to 1 and 2, then you have to start your game again, basically. Like, something's happened here. Gamma equals 1 is bad. Yeah.
Because they cancel each other out?
Gamma equals 1, you're in all sorts of trouble. I mean, you could fix it up with L'Hopital's rule, it's true, but you'd start some of your calculations back here. You'd go back. What's that?
Between 1 and 2, the C over N will dominate on either side.
That's right. It's different. Right. Right. So, yeah. So there should be a piece here about gamma being between 1 and 2. So if that's the case, then yes, this is the dominant piece. Right? Yeah. So that's the thing. And then these ends will cancel. The C is on the bottom, so there's 1 over C here. And if you undo this thing, which we could do, so it's gamma minus 2 over gamma minus 1 and times 1 over C. The ends have gone, so it's 1 equals this times 1 over C. So we can put the C on the other side. And this is going to be gamma minus 1 over gamma minus 1 for gamma minus 1. Right? So this stuff is just 1. So we can have, I'll put this on this side, 1 over gamma minus 1. This guy on the other side, 1 minus C. It's possible I've got it all wrong. And then flip it upside down. So this is going to be gamma minus 1, 1 over 1 minus C. And we'll put the 1 on the other side. That's surprising. Okay, so so if C is small and getting close to 0, then it goes to 2. If C is, you know, a little more than, yeah, then it's above 2, isn't it? Okay, I'm going to have to think about that. Yes. Okay, I'll check this. So something needs to be fixed up here, but this is the end product for small. So for small c, you're going to get gamma close to 2. Yep. Okay, I'm going to have to figure that out. All right. Homework for me. Okay, so I know this is the end part. That's changing. So we put a floor on the thing. If we mess around with this and do something different and not let everyone start at the same time, which is obviously a bit of a strange thing to do as well. So we allow these firms to have lived for a different amount of time. So one way to do this is just simply to put in some probability distribution for their ages, right? So this is a very simple one. This is just really just for exponentials appear, right? It's a random failure story. So they're quite natural. So we're going to put in that probability distribution, just as an example, but in general, you could mess around with all sorts of things. So there'll be no bottom limit. You can have the xi's following a log normal. So they're actually all still, they're not competing anymore. They have log normal size distributions, which grow as a function of time. But they've lived for different amounts of time. So the probability that your randomly chosen firm has size x, well, here's your power law, here's your log normal distribution for its size. And then you have to multiply by the probability that it has been around for time t. Right? So the probability that it is of size x, that it's been around for time t, and integrate over that. Right? So x is a parameter in here, it's not. The integral is over t. So this seems like this is a simple thing. Right? We've just included a different ingredient. We've thrown away the one of the having a floor away from 0. We've gone back to just plain log normals, but now they're of different ages. So that seems like a very simple thing to do. So there's a fun integral to work on. And I'll step you through it. I mean, it actually took me a few years to figure this one out, but I'll give you a way of dealing with this. So there's a lot of magic involved in figuring this out. It's very enjoyable. Integral foo. Okay. It really is quite silly. Okay, so you're averaging log normal distributions, right? So you're averaging over these things. It turns out, so you'd think, okay, maybe it gives us something slightly different. It gives you this, okay, you have to do that. It gives you this oddness, right? So you get a 1 over x, and then you get e to the minus the square root of a beast here, which has lambda, a parameter. Log n of x is in there, divided by m. So what's going to happen is, it depends on, there's a square root of a square. So if we do this correctly, it depends, if this is a positive quantity, then we just take its square root. We can just rewrite as log x over m. If it's negative, then we have to explicitly put the negative in, right? Because we're squaring it and taking the square root. So that's x over m. So if x over m is greater than 1 or less than 1, then we have a transition. Okay, so this x over m. So that's, maybe I should make it log of x divided by m, right? So it's this. It's really this, if that's not obvious. Log of x divided by m. Okay, that's not obvious. Yeah, I'll fix that up. So when we take this square, if we want to replace this, so you're going to actually have a change in the way this works. It's going to be e to the minus plus or minus log x. Okay. So if log of x over m is greater than 1, then we get simply e to the minus, and it's the square root of 2 lambda. That's got to be there, And then this piece is just going to be replaced with just log x over m. If log n of x over m is less than 1, then we get e to the minus root 2 lambda. We get this, plus. Yeah. All right, now all of this, there's an e to the root 2 lambda here. Yeah, so this is going to pop up here, right? I'm going to put this up here, root 2 lambda like that. This is going to pop up here, root 2 lambda. So it's e to the minus ln, and in fact, we'll make that a minus sign. So it's e to the log n of x of this whole blob. So e to the log of a blob is the blob. So now we have x over m minus root 2 lambda. And in this case, we have the same thing, but it's got a plus sign. So that's pretty weird. You get a different exponent on either side. You get a break in scaling, right? This happens a lot in things. You've seen it with the Google, the Google data set. So it looks like -1, and then you get plus or minus these pieces. So it's going to actually have this change in scaling. Right, so it's going to be a bit of the scaling is actually going to be -1 plus root 2 lambda here, and then -1 minus root 2 lambda. So this is really odd because it's actually greater than -1. But it has a break, and this is around x over m. And then it becomes a reasonable exponent. This is less than, it's steeper than -1. So it's sometimes called double Pareto. Montreal and Schlesinger, notice this is a while back. Did lots of nice things with these kind of random growth things. And then this work was used again, obviously, and used lots of other places, but this is the number of pages per website. I think it's that work. They did one piece where it was the number of pages that people looked at as they went into a website and then went somewhere else.
So wait, what's the relation between this standard Pareto, not a Pareto from something else? Right?
Oh, that's another thing. Yeah. So this is used as an explanation for why, right? So it's you have websites of different ages, and they're growing like Lognormals, right? Yeah, well, each one is just growing according to some Lognormal distribution, and they're all obeying that same Lognormal distribution, but they have different lifespans, or they've been alive for different amounts of time, according to an exponential distribution. So they use that to to produce this kind of output for the actual number of pages. All right, so they have a break. Again, it's a mechanism that you could go in, and if you have enough data, you can see if this is actually at play. All right. Scary business. So you can certainly get this mixture between, this confusion between lognormals and power laws. Bible distributions are in there, all these other guys. You get lognormals from these random multiplicative growth models. If you put in a minimum size, in a particular way at least, analytically, you get a power law tail, which is odd. And it has a tunable exponent. And if you take that minimum size away, but put in a distribution of lifetimes, then you get this double Pareto. So it's it's crazy business, right? So there's a little bit of fickleness in this. I mean, we're always in science trying to find universal stories and so on. I mean, or at least trying to find the extent to which something is true. So there's some sensitivity here, right? So basically be careful. Yeah. Okay. All right. That piece had to be there on the end. I can't not tell you about these things.
You can also not be careful and get published.
It's a fair call. Yeah. Right. Okay. I'm going to just tell you a few of the, we'll just start off this business here. A little bit of inspiration. Okay, so this is good. Networks. So networks, there's a lot to talk about here. There's just there are network models. There are measurements of networks that matter, right? So there's all of graph theory. We measure certain sorts of things in graph theory. In growing networks, in real networks, there are different. It turns out there are different properties usually that we're interested in, right? And there's one giant one, like an elephant in the room, that basically no one's looked at ever until recently. Worry about this guy. Yeah, that's better. Okay. Thing. Okay. I'll just tell you a few things, right? So networks, there's a nice history to this, and maybe that's what we'll do today. Right? You have senses of things. So there's the actual physical things. And here we have the word, right? Complex systems of roads. This is where it starts with railroads and so on, transportation. So it's actual physical things. We started to then lift out into things like network television, how people connect themselves, of course, and machines. So there's this kind of nice lifting of this metaphor for the, using sort of metaphors out into the real world. Of course, networking is a thing we do. So, lots of good words here, right? The web, of course, lattice, net, matrix, mesh, these are good words. Reticulum is a ridiculous word, but that's a good Latin term. So maze, labyrinth, this is very exciting. These are great words. Okay, good. So Keith Briggs is actually, he was a postdoc back in Melbourne when I was an undergrad, and he's done lots of interesting things. I think he works with British Telecom now. So he did this nice little, put this on the web, little etymological thing. So opus reticulatum, so work made of a net. And so here's an example. This is brickwork, right, that's laid out in a kind of a web story. It's not actually set as a network, but this is where at least we think some of the earlier stuff comes from. Right, so great like a network of brass, right? There are these uses as we go through history. So again, as I said, we're lifting out. This is people doing bad things, dissecting animals, right? So reticulate structures, used there. 1839, we started to talk about rivers. We started to sort of appreciate them like this. Railways, which we built. Electrical cables, again, things we built. Wireless broadcasting, right? So we started to kind of lift this story out. Lots of, these both have very nice, so net comes from spiderweb, actually, which is quite nice. So it's 888. And work, of course, is stuff that we build. So, ironwork, stonework, fretwork. So it's quite a sort of practical, working kind of word in a way. So anyway, there's a history of these things. You can check these things out. Okay, so here's the big deal, and so we'll start off with this. So many of these complex systems have networks underlying them, maybe layers of networks, and of course many of them really have layers of networks if you think about infrastructure and different kinds of networks, different kinds of materials being moved around, and then people acting in different ways. They're always layered things. But this kind of realization, this kind of concrete, this concretization of the problem really opened the door, right? So people just took off. If you look at the early 2000s all the way through even till today, computer scientists have been adding a lot of stuff, of course. Tremendous amount of work now, I think. So there's a lot of theoretical physics kind of StatMech approach. Right? So this is the stuff where we can at least understand it, describe it, do a pretty good job. We can write down little models and get a reasonable flavor for it. I think there's, again, this sort of thing we've talked about, this transition to computer simulations and so on that may be a little more inscrutable, but get the job done. Machine learning things, all sorts of stuff. There's been a ridiculous amount of stuff published. Now it's just way too much. It's just way too much. There's no way you just cannot, you need other people to filter. So collectively, we're all sort of filtering it, and things are bubbling up, and we know that doesn't work all that well, right? Some things succeed. The possibly shouldn't have, and many things get lost. So anyway, we're in that kind of struggle right now. So the kind of people involved are these piranha physicists, right? They tend to hunt in packs and they jump on a problem. So things like cellular automata, all sorts of other stuff that they've ripped to shreds. So it's also a bit like little kids playing soccer, right? The ball jumps out and they all go jump on it, and they go and jump on that one. So they are, what's left at the end is not very pretty. Just sort of they eat the whole thing. Okay, I'll finish with this, and I mentioned this at the start, so this is a good place to finish. So, Duncan, we've heard from Strogatz a few times in the course already. So this is a paper that appeared in Nature. I'll tell you some more about it next time. It's been cited 20,000 times. And so that's 98. 99, we have a paper in Science by Barabasi and Raker Albert. It's getting up there, 18,000. This one's, they're both huge for their own reasons. This one turns out to be Herbert-Simon's model. Not exactly as good a version. We've talked about preferential attachment. This is the preferential attachment model. But again, data was the story, right? So both of these are data-infused things, right? The actor graph is in this one, which is kind of ridiculous, right? You take every movie, and if two people are in a movie together, then they're connected. So you make this funny network. They have a power grid. Power grid is in here as well. And they have C. elegans, which has 290 or 1 or 2, neurons in it. It's not a very big network. But from those 3 here, and they have 2 or 3 as well, like the Notre Dame website, they're able to show a bunch of things about real networks. This one is structural. We'll see it has some interesting follow-up, right? Because it's about why some networks are small worlds, right? So this idea that many networks are in fact like this. So it's the idea that no one is very far apart from everyone else, right? So the 6 degrees of separation story. Stanley Milgram appears here, is very important. I'll tell you a lot more about it. It turns out that this is only about the structure, and there's all this work that came after, which is about the algorithm you need, right? So you need to be able to search, right? It's not enough just to have a network that in principle is searchable, like you're only 4 steps away from someone. You have to have an algorithmic way of doing that, right? Then there's a third layer, which is, can you influence someone that far away? And the answer is probably no, right? So you could be 6 steps away from the president, but good luck. 6 seems like a small number, but it's huge. Okay, so that's where we'll really dig into these guys. The first thing that will come along, by doing this, I'm trying to say that this is a big field. This is a giant field, and these things really matter, right? So we're going to have examples of complex networks, properties, and then the next set of slides will be about models. And that'll be these 2 guys and a few other pieces. All right, so there we go. Move through a few things. We're on to networks, which is awesome. Okay? Awesome.